I will talk about my work, my postdoc work concerning the optimization of a particle in cell called warp. And I will explain in more detail different tricks to improve particle in cell codes in general. It works. So first, what's particle in cell codes? So particle in cell codes are methods that solve kinetically collective interactions between plasmas described by charged particles and electromagnetic fields. Particle in cell codes have different applications: plasma physics, laser matter interaction, and particle acceleration. This is the case of the PIC code warp developed at LBL. And here you have several snapshots of different simulations performed with this code. So in order to provide to warp high-performance subroutines, we have created a high-performance library called PICSAR, designed so to be interfaced with the PIC code warp, but not only. It will be soon released as an open source project in order to provide the community high-performance subroutines for any PIC code. And warp is one of the selected code of the NERSC Exascale Science Application Program, so NISAP at NERSC. So just to answer the question of the referees, what's unique about my tuning jobs? My tuning work, sorry. So first, I'm running my code only in cluster mode, mainly on Curie Phase 1, equipped of Haswells, and the NERSC white box equipped of KNL. For debugging, I'm mainly using Alinea DDT, and for profiling, I like using Intel tools like VTune, SDE. I will explain how, and also Advisor and Alinea Map. We also have some collaboration with Intel via the Design Forward project with Anthony Nguyen and Karl Beckman, but also in the framework of the Intel Advisor Roofline tool with Zakhar Madviv. So in this presentation, I will first describe briefly how works the particle in cell method, describing the data structures and the main PIC loop. Then I will turn to the performance bottleneck and describe the optimizations we have added in the code to solve them. And in the last part, I will speak about the overall performances. So let's start by the data structures. So in PIC codes, we first have to describe the fields. So with the finite difference solvers that we are using, electric field, magnetic field, current, and charge are discretized as regular Cartesian grids, as described here on the figure. And each field component, x, y, z, of each quantities here will be stored in a 3D double precision array. Typically, with such a finite difference scheme, solving the Maxwell solver is a stencil problem. Then we need a data structure for the particles. So here, plasmas, so the world of the matter, is described by macro particles, which are groups of real particles having the same kinetic properties. We do not describe directly all the real particles because there are too many of them, and it would be too much expensive computationally. Each macro particle is described by, each macro particle property is described by an aligned 1D array. Typically, it's like doing a structure of array for each property: velocity, position, energy, weight, and field. And this is crucial to get an efficient vectorization. Now, before going to the description of the main loop, I just want to speak about the most common parallelization. Usually, PIC codes are decomposed into space subdomains, and each subdomain is handled by one MPI task. Each MPI task has its own local grids and particle in cell, and particle property arrays. And in PICSAR, we use the Cartesian topology operator in MPI. So the typical PIC loop, the most basic PIC loop, is divided into 4 parts. The first one is what we call the charge and the current deposition. Typically, when the particles are moving or when they are existing, they are creating a charge, a local charge, and a current. And this current is deposited on the nearby nodes on the grid. Then we have to solve the Maxwell. We have to update the grids via the Maxwell solvers, and for this we are using the current deposited just before. Then we have another interpolation step as well as the first one, which is almost the inverse of the current deposition. Here, from the nodes on the grid, we'll determine the field seen by the particle at its position. And finally, thanks to the fields, we can push the particle forward. We can move the particles. So let's now turn to the performance bottleneck and the optimizations. So a first thing we have done is optimizing the memory management. So for this, we have implementing what we called the tiling. The tiling is nothing else than a cache blocking technique. It consists of dividing each MPI domain into sub-blocks called tile. We can also call them patch or blocks. Some other teams are calling them like this. And each tile has its own local grid and their own local property arrays. So thanks to the tiling, we can improve the memory locality and have an efficient cache reuse. Cache reuse only if we have certain conditions. The main constraint is that the local tile field grid should fit in the L2 cache on KNL or on Haswell. And because on Haswell we also have L3, we can expect in some test case or in some simulation to have the particles arrays entirely in the L3 for one tile. Then we have added an OpenMP parallelization inside the MPI. So an inner node parallelization in a sense. And when we have much more tiles than threads, we have a load balancing between the tiles, which is an interesting point for OpenMP here, contrary to keep only MPI. And this is highly generalizable because it can be applied to any structured grid with particles or unstructured grid with particles. So I will present different performing tests or benchmarkings. And for this, I will use one test case, an homogeneous thermalized plasma, which has the good property to have a perfect load balancing. It means that we have the same amount of particles between all the MPI and all the tiles. And in the result I will present here, the problem entirely fits in MC-DRAM for KNL. And I will present some tests on two systems, so Curie phase 1 with 2 Haswell processors per node, and one KNL of our white box, a 64-core KNL configured in SNC4 flat mode. I will use two configurations for the test. The configuration 1 for the non-optimized version of the code with only MPI, and the configuration 2 for the optimized version using as many MPI as we have NUMA domains, and then I will fill the rest of the cores with OpenMP threads. Except that on KNL, I'm using hyper-threading, so 2 threads per core. So here are the results for the tiling plus OpenMP. So here on this figure, for the coordinates, we have the Speedup. We can divide the figure into 2 parts. A first part for Curie phase 1 and a second part for KNL. And then each part can be divided into 2 subparts. A first part for order 1 interpolation and order 3 interpolation for the interpolation steps. Then we have 4 colors, the blue for the kernel being the entire peak loop without the initialization and the diagnostics. The current deposition in red, in green the field gathering plus the particle pressure all together, and in orange or yellow the communications. So first, what we can see is that the tiling has, the tiling speed up significantly the current deposition and the field gathering, which are the two interpolation steps. However, due to the addition of the tiling, we have a new particle exchange step, which means an overhead, and this becomes the new hotspot of the code. Finally, we still have a speed up for the entire kernel, but we have to optimize the particle exchange. So this is the next step. Let's describe why we have an overhead due to the communication, due to this new communication. First, we have an overhead because we just have new things to do, so a new communication pattern. Then we have some redundancies because what we are doing to pre-process the particle that will leave or not the tiles, we are doing the same thing for the MPI domains. So we are doing almost 2 times the same thing, and then the process is still sequential. And the problem is that we cannot apply a naive parallelization because if we let OpenMP manage everything by itself with any scheduler, potentially when the particles will arrive in the same tiles from tiles around, for instance, they will try to access the same memory location, so we will have memory races. So what we have done to optimize the communications, first we have merged the pre-processing loops between MPI and for the MPI and the tile communications. We have local and global buffers to perform a single exchange for MPI. We do not use threaded communications. In fact, we have an implementation, but for the moment we still have some bugs with it. We added an OpenMP parallelization for the communications, and for this we are using a block structure. So block structure of 3 by 3 by 3 tiles in 3D or 3 by 3 in 2D, as shown here on this figure. And we perform simultaneously the communication for one particular tile in each block. So for instance, first we perform the communication for the first tile, then the second one, and so on until the last one, so that there is always 2 tiles between exchanging one, between active ones, and we will never have any memory races during the communications. This enables to have a nice speed up for the communication, 2.3 on Haswell and 4.6, well, it's around 4.6 on KNL. For the last optimization, I would like to focus on vectorization. So one of the bottleneck, the main hotspot of the code for the vectorization is the charge and the current deposition. These two processes, in fact, so first I will remind you what I mean by charge and current deposition. So the charge and current deposition is when the particle deposits on the nearby vertices of the grid the charge of the current they have generated. So, in fact, if we take the classical algorithm, we can divide it into 3 parts. First, we have to determine the nearby nodes on the charge, on the grid, so for the charge of the current, compute the charge or the current at the particle location, and then deposit, thanks to an interpolation process, the contribution to the grid. So the step 1 can be well vectorized, except that we have conversions and roundings. The second one is fine, but for the third one, we have a problem because when 2 particles are located in the same cell, they will try to access the same node. So for the vectorization, it's a problem. Then we also have some problem with the efficiency because the grid nodes are not aligned. So we can potentially have many gather and scatter during if we apply a naive vectorization. So the idea here has been to change the data structure. So to come from the original one with a Cartesian grid to a new data structure with a new dimension here that will contain the 8 vertices that are supposed to get the particle charge of the particle current. Because the 8 nodes are aligned in this new dimension, we will avoid gather and scatter operation, and we will also avoid memory races because we will change how the parallelization is done, how the vectorization is done. So we keep the first and the second step as it was before, but for the vectorization, we do not apply it on the particle loop, but we directly apply it on the deposition process. So each particle will deposit in a vectorized way its charge or its current on the 8 vertices. So this has a good advantage to provide an efficient, but also to enable vectorization, except that we have to reduce this structure to the original one at the end. The good news is that here the complexity of this reduction is just in number of cells, and there is much less cells than number of particles. So the complexity of the reduction is much less than the complexity of the whole algorithm here. So here are the speedups for the current and the charge deposition, the new algorithm. Here again, we can divide the figure into two parts, phase 1 and KNLs. Then again, divide each part into order 1 and order 3 interpolation. We can see that we have speedup between 1 and 2. In fact, I ran this simulation a few weeks ago, and I was surprised to see that we now have numbers a little bit less that we used to have before. So I need to understand why. Originally, this was giving speedups around between 2 and 3, depending on the charge of the current and the order. But we still have speedups here. So let's go now to the last part, the performance, the overall performances. So again, we have the same structures of figure, except that here I'm plotting the time and not the speedup. We can divide it into two parts, Corey and KNL. But here, the two parts concern the non-optimized code and the optimized one. For the colors, we have in blue the kernel, in red the current deposition, in green again the field gathering and the particle pusher, in orange the communications, and now we have in purple all the other steps or the other subroutines. I mean the particle sorting, the Maxwell solver, and the charge deposition. What we can see first is that without all the optimizations we have made, simulation time is 1.4 longer on KNL than on Haswell, for the original code, I would say. Then, thanks to the, thanks to the different optimizations, we can get a speedup of 2.4 on Haswell, but 3.7 on KNL. And with the optimization, at the end, KNL performs better than Haswell for the order 1 interpolation. Here it's only for order 1 interpolation. So the conclusion is that the implemented optimizations are essential on KNL to reach Haswell performances. But optimizations are also very interesting for previous architectures, such as Haswell or EV Bridge, because we also have, because I also performed, I did the same thing for Edison, our cluster equipped with EV Bridge processor. So now we have the same thing, but for order 3 interpolation. Here we almost have the same results, except that before optimization, the KNL was 2 times slower than on Haswell. I should mention that order 3 interpolation is usually used in real production simulation. So this is more significant. This is a more interesting result than order 1 in a sense. Here, thanks to the optimization, we have only 1.7 speedup on Haswell, but we can see that we have 5 a speedup of 5 on KNL, which is very significant. We were very happy when we get this. And it's really important because we can see that without this, we were really bad on KNL. I wanted to present you some roofline results for PICSAR, but I won't have the time to do this. So I'm using this slide to advertise the tutorial presentation of Jacques Deslip tomorrow on how to optimize code using the roofline model. And I will present this slide tomorrow with some other results. So to conclude, what we recommend from PICSAR for PIC code in general, and maybe for many codes, much more codes. First, we have to simplify the loops. In fact, I didn't mention it in the speedups, but just by removing the branching inside the very intensive loops gave me a larger speedup than many of the optimization I have presented here. So it's really essential to change the loops and to simplify them so that you only keep the essential, and it's better to use specific subroutines with branching outside the intensive loops. Then I recommend to focus on the memory management using cache blocking techniques to improve the memory locality, and we'll use L2 or L3 on as well as also. And then to focus on vectorization and to not hesitate to change the data structures, even if sometimes it can be tricky for some algorithms. So here our most useful optimization tools are VTune and NSD for the calculation of the roofline, and Advisor for checking vectorization. I will show it tomorrow. The challenge we still have are optimizing the field gathering. It's not perfect for the moment, particularly for higher order interpolation. Understanding register splitting issues. This is something that I have with Advisor, and I'm still trying to understand this, to try to find solutions. So I can discuss with somebody about this if you want. And then we need to improve several other algorithms in the PIC code, not in the basic one, but in more evaluated PIC codes. And the next step is to try all these optimizations with several nodes, not only one node on KNL or one node on as well. Thank you. Thank you for your attention.
Question, people.
Have a separate allocation for each tile, so a separate array for the particles in each tile. Is that right?
In fact, for the fields, we still have global arrays but just before doing, for instance, the current or the charge deposition, we will just pass as an argument. In fact, we'll create a structure, a local structure, and we'll copy the information that we need from the global arrays to this structure, so that only the structure will be contained in the L2. So we still have allocation for the tile.
The particles, though, you said that you have to pass particles from one tile to the other. So is there one global array of particles, or is there a particle array for each tile?
Oh, sorry. There is one particle array for each tile.
How do you size that?
Why?
What size do you allocate for those tile private arrays?
So at the beginning, there is a user-defined size, or not necessarily by the user, but there is a size. And if we reach 60% of this size, then we have a reallocation process to extend the size in case of we reach the maximum size. Just for the tiles. It's only for the tiles. Because in fact, we do not have global particle arrays anymore. So now we only have local particle arrays. Only the fields still have global arrays. So we can just decide to reallocate the fields in a particular tile and let the other like they were before. we were more worried when we were only using MPI than now, because now, thanks to the tiling, let's imagine a tile has more particles than the other. Thanks to OpenMP, we'll have a natural load balancing. I mean, one thread will compute maybe during a lot of time for just one tile, but all the other threads will handle all the other tiles with less load. So, and I should also mention that we have a load balancing algorithm also to exchange to exchange load between the tiles in case of there is a huge difference of load between them.
How would you handle a pathological worst case where all of the particles are in one tile, they hit the 60% bound, and you increase the memory for that tile, and then all of the particles move to another tile, and that keeps happening?
So you mean, for instance, a beam traveling across the domain? So this is a particular case, yes. And in fact, we are still thinking that we'll have more than one tile to describe one beam, because even if a beam can be very small, tiles are really, really small. And we have some constraint on the mesh, which means that if the beam is contained in the tile, probably we are not discretizing enough our space to have an accurate simulation. But it's a problem we have to think about. That's true.
Other questions?
So got two questions. One question that you mentioned about the kernel, the iterations between the update of the field and also push the particles. So you kind of simulate this movement of particles in real space, right? Now in momentum space. So
yes, it's in the real space. I mean, it's not like an Eulerian discrete vision, like you're solving both your particle in a distribution domain with momentum and position. Here, yes, it's really a kinetic description with existing particles.
Okay. The second question is, so you mentioned about the load balancing with OpenMP. How you use OpenMP for the load balancing?
Oh, in fact, it's just because we have a lot of tiles, and we have a smaller amount of threads. If you use, for instance, a specific scheduler like dynamic, the charge will be distributed between the threads, and if a tile is particularly heavy to be computed, so it will be computed during a lot of time by one thread, but the others will continue to handle the rest of the tiles. So this is just a natural feature of OpenMP.
Yes. Nope. Okay. Well, thank you very much, Mathieu.